Types of aqueous solutions. Let's think about two aqueous solutions that we have encountered in the kitchen. Salt water and sugar water. Both of these are homogeneous mixtures. You put a teaspoon of salt in some water and stir it up, looks like water. You put a teaspoon of sugar in some water, you stir it up, looks like water. They don't taste the same though, do they? The substances seem to disappear, but they're not. They're just mixing on a molecular level. So how do solids dissolve in water? We know that salt dissolves in water, but sand doesn't. Why? Pepper doesn't. So when the solute is put into a solvent, there are competing attractive forces. And whether the solute dissolves or not will depend on relative strengths of these forces. So here we have represented as purple balls our solute. So this might be the sugar or the salt. There are attractive forces between those molecules. We'll talk more about what exactly those are. If you remember from Chem 3A, those are the intermolecular forces. Those hold these things together. That's the reason that salt is a solid sitting in your salt shaker, because the particles inside the salt are held together by attractive forces. There are forces that attract between the water molecules. That's why the water stays as a liquid and doesn't turn into a gas. And when we put these two together, we have the potential for attractions between the solvent molecules and the solute molecules. So those attractive forces are a little bit like the forces of attraction between people. You have some people that you're really, really attracted to, right? You want to spend all your time with these people. And there's other people that you're actually repelled by, and there's some that you're like, oh, I kind of like you okay, but if I see this other person, I'm going to go off with them, right? You can relate to that. Same sort of thing is happening here with the particles. So these particles came in here, and they really, really like each other. There wasn't really anybody else for them to be hanging out with, but they really, really like each other. So then when they come in here and start mixing with the water, if they are really attracted to the water, then they're going to mix really well. If they're not very attracted, they're going to kind of clump together. So all of my ancestors came from Sweden, and all of my husband's ancestors came from Japan. So I can talk about those two nationalities and not be accused of anything, right? So if these are all people who only speak Japanese, and these are people who only speak Swedish, are these people likely to mingle with each other? No, because they can't communicate, right? And communication is a big part of attraction. So what would happen, you can imagine what would happen in a room with two large groups of people that do not share a common language. The people who speak Japanese are going to be in little clusters, and the people who speak Swedish will be in little clusters, and they will not interact with each other. That make sense? That can happen with solids and liquids as well. What are some of these attractions? So we have to get kind of a preview of this. Water is a very special molecule, so we need to understand a little bit about water. So water is an oxygen atom and two hydrogen atoms. There's an uneven distribution of the electrons. So this is held together by a covalent bond where two electrons are being shared between an oxygen atom and a hydrogen atom. They're not shared equally though. Oxygen is bigger and she hogs the electrons. So it's like sharing a cookie, right? You have two kids and you tell them to share the cookie, right? When one kid is 10 and the other kid's 2. So the 10-year-old's like, I'm going to break this cookie in two, but I'm giving the little piece to him because he's little and he doesn't know any better. So hydrogen is getting the short end here, the small piece of the cookie. So there's an unequal sharing here. That makes the oxygen end a little bit negative and the hydrogen end a little bit positive. It's not an ionic bond where the electrons have been transferred. They're still being shared, but not very equally. So it's a partial charge. And that happens with this other bond as well. So the water molecule has a negative side and a positive side? Well, if we're trying to dissolve sodium chloride, the sodium ions and the chloride ions are very attracted to each other by ionic bonds. Opposite charges attract very strongly. In order for the sodium chloride to separate from its pals and go out into the water, those forces of attraction need to be replaced by something similar in strength. Well, the sodium ion is attracted to the negative side of the water molecule. This isn't a full negative charge, it's a partial negative charge. But there's attraction here. The chloride ion is attracted to the positive side of the water molecule. And so the water, I imagine the water molecules, here it's bringing its positive side to the negative ion. Hey, come on, come out and play with us. So like luring them away from the family or something. You could go all sorts of strange ways with that. And here's water turning its other side to the positive ion and say, hey, come out here with me. Well, we can't replace this full positive negative attraction by pairing up with one water molecule, but there's a lot more than one water molecule. And so what happens is a bunch of them will cluster around the ion. And so now this positive ion is feeling an amount of negative charge around it that's comparable to the amount of negative charge it felt when it was part of the sodium chloride solid. And the chloride is feeling the love from the water molecule over here. So the water molecules are making up for the forces of attraction that are lost by the ions separating from each other. Does that make any sense? Chemistry is full of a lot of very abstract things. And my feeling is anytime that we can relate them to human behavior, we have a much better chance of remembering, right? Because I don't know about you, but when I take an exam, memorized facts tend to just leave my brain, right? They just fly out. We don't even have I guess we do have a window, but it doesn't open. They fly out the closed window and they're gone. But if we can think about it and imagine pictures and what might be going on, then we can reason out the answers, and that's a lot more effective in the long run than memorizing stuff. So, the water molecules come around and they lure the ions away. What the result is, we have ions, charged particles, that are free to move through the solution. Charged particles can conduct electricity. Electricity is the flow of electrons, and these charged particles can carry electrons through the solution. So a solution in which ions are formed when the solute dissolves is called an electrolyte. An electrolyte here is referring to the same sorts of things that they talk about when you're exercising and you need to replenish your electrolytes, right? And they're trying to sell you all these expensive beverages. Your body needs a certain amount of salts, not just sodium chloride, but other things as well, magnesium and all these different ions. When you sweat, you lose those salts in your sweat. That's why if you sweat really hard, your shirt, when it dries, will have those white things on it, because that's all the salt that came out of your body. Well, you need to replace that to stay healthy. Electrolytes will conduct electricity. Your body uses electricity for various things, and it needs those ion concentrations to be right so that it can function correctly. So electrolytes would include all soluble ionic compounds. When those dissolve in water, you've got charged particles. You can also have solutions that do not conduct electricity. These are called non-electrolytes. And these would be most molecular compounds. Things like sugar. When you dissolve sugar in water, it does not form any ions. It's not going to conduct electricity. The sugar molecules remain intact. So here's an illustration. If we take deionized water and put 2 electrodes in it and connect the electrodes to a light bulb and a battery, when it's just pure water, the light bulb will not light up. If we add salt to the water, the salt separates as it dissolves into ions. The ions are able to carry the electric current from one electrode to the other, closing the circuit, and the light bulb goes on. If we do the same thing with sugar, the light bulb will not light up because sugar does not form ions. It's a non-electrolyte. It cannot conduct electricity. So what happens when sugar dissolves in water? Well, sugar is a polar molecule. We've got oxygens and hydrogens, and those hydrogen-oxygen bonds are unequal shared electrons, just like they are in water. So this oxygen is going to have a little bit of a negative charge. That's going to be, it's pointing to this one. The hydrogen is going to be partially positive. That'll be attracted to the partially negative part of this water molecule. Here, hydrogen attracted to oxygen. Here, the oxygen on the sugars being attracted to the hydrogen on the water. So again, we've got these water molecules that are going to come around and make the sugar molecule feel comfortable. It's going to be attracted to them. So we talked about acids, and we learned how to name them and write their formulas. And we said that acids are, we didn't say that. Acids are molecular compounds that ionize when they're dissolved in water. So an example would be HCl. HCl is hydrogen chloride or hydrogen monochloride. It's two nonmetals. It's a molecular compound. But when we dissolve it in water, it forms ions. So the water effectively pulls this apart, and now we've got hydrogen ions and we've got chloride ions. So there are two kinds of acids, strong acids and weak acids. A strong acid ionizes completely. All the molecules separate to form ions. In a weak acid, only a small percentage of them do that. A few of the molecules form ions, but most of them do not. So HF is an example of a weak acid, hydrofluoric acid. And so here, this arrow has a head on both ends instead of this one that's only pointing to the right. The arrow pointing to the right indicates that the reaction goes in this direction only. Here we have a double-headed arrow, means that the reaction's going to go in both directions, and it's not going to go completely to one side or the other. How far it goes is another topic that you'll deal with in Chem 1B. Here's another acid. This is the acetate ion with an H in front of it. Acetate becomes acetic acid. That separates into ions, but only a little bit. So here we have an illustration of an acetic acid solution. Acetic acid is the acid in vinegar. So we've got a lot of these intact molecules, and we've got just a very few ions. So there's an acetate ion and a hydrogen ion. Here's another hydrogen ion. These are hard to look at. There's got to be another, I think it's maybe this one. There's got to be another acetate ion in there. But most of them are still molecules. So strong acids are strong electrolytes. They form ions. They conduct electricity. Weak acids are weak electrolytes. They're not non-electrolytes, but they're weak. They only form a little bit of ions. They only conduct electricity a little bit. Yeah, what I just said. So here's a picture. I like pictures. So non-electrolytes such as sugar, you put that into the water, light bulb does nothing. Does not conduct electricity. This is a non-electrolyte. Here's a strong electrolyte, sodium chloride, ionic compound, it's soluble, you stick that in there, lots of ions, electricity flows. Bright light bulb, strong light. Here we've got acetic acid. This is a weak acid, which is a weak electrolyte. It only ionizes a little bit. So the light bulb glows, but this light is weak, because it's having a hard time getting the electricity through the water because there's only a few ions to carry it. So a weak electrolyte will conduct electricity weakly and give you a weak light in the light bulb. So we were just talking about molecular compounds that ionize in solution. Those are the acids. So what happens with ionic compounds? Ionic compounds don't ionize, because ionize means to form ions. An ionic compound already has ions in it, so we say that they dissociate, meaning the ions are there, but now they're going to separate from each other. Associate means they come together, dissociate means they go away from each other. So this compound, sodium sulfide, we can write an equation for its dissociation. We're going to just separate this into the ions that it would form. And we learned how to do this when we learned how to name them. So here we're going to have two ions, sodium ions and sulfide ions, and we can predict their charges from position on the periodic table. The formula tells us how many of each. Na2 means 2 sodium ions, and I've got 1 sulfide ion. Compounds that have polyatomic ions, the polyatomic ion will remain intact. So all of the things that we write equations for dissociation, there will only be 2 ions. 1 cation, 1 anion. Okay, other things exist, but we don't have to learn about them. So here's sodium sulfate. There are 3 different elements here, but it's still 2 ions. The sodium ion and everything else, the sulfate ion. Okay? So the ionic compound dissolves in water, the ions dissociate, and we have an electrolyte solution. But not all ionic compounds dissolve in water. Sodium chloride does, but calcium chloride doesn't. How do we know? Well, in simple terms, we can say that a compound is soluble if it dissolves in water, insoluble if it doesn't. And those are qualitative terms. So soluble means it dissolves, insoluble means that it doesn't. But the truth is that even an insoluble compound dissolves a little bit. It just doesn't dissolve enough to be important, okay? It might be 2 formula units that dissolve in a whole beaker full of solution. Yes, some dissolved, but not enough to be important. So we say it's insoluble. So soluble versus insoluble are sort of practical definitions. Silver nitrate. You can look at the formula. There's the silver ion and the nitrate ion. This will dissolve in water and form a strong electrolyte solution. All of the ions will separate. They will dissociate from each other. We have silver ions and nitrate ions. Silver chloride, on the other hand, is almost completely insoluble. We say it's insoluble with, the caveat that some of it dissolves, but just a little teeny tiny bit. So you put silver chloride in solution, and the silver ions and the chloride ions are like, so we're good here. We're just going to hang out together. We don't want anything to do with the water. We just don't care. And it's not going to dissolve. Now, it's very complicated, the factors that explain why sodium chloride doesn't dissolve. That's not sodium chloride, that's silver chloride. Silver chloride doesn't dissolve, silver nitrate does. It's complicated. So instead of spending a lot of time trying to understand the factors behind that, we're just going to learn what's called an empirical method. People have tried these things, okay, let's put some sodium chloride in the water. Okay, that dissolved. Let's put silver chloride in the water. No, doesn't dissolve. Make a note of that. Okay, so people have done a lot of this and noticed some patterns, and so that's what we're going to learn about. Some rules based on experimental results. So this is the table. Solubility rules for ionic compounds in water. Now, I know you guys like those green and yellow cards that the department has, and on the green card are solubility rules. They are slightly different than the rules here in the book, there's more stuff on that table. This is what you need to know. So you need to know this table. That looks a little overwhelming, right? There's all these letters and some words and stuff. It's really not that bad. So the table is divided into two sections. The top, these are compounds that are generally soluble, and then there's a list of exceptions. In the bottom, compounds that are generally not soluble, and some exceptions. And the way you approach this is you start at the top of the table. So at the top of the table, lithium, sodium, potassium, so those are group 1A metals, and ammonium. If it's got one of those in it, it's soluble. No exceptions. You don't have to look at anything else. You're done. It's soluble. If you don't have one of those, then you continue to the next row. Nitrate ions and acetate ions. Does it have one of those in it? Then it's soluble. There are no exceptions. If that doesn't cover it, then you go to the halides, chloride, bromide, and iodide. Those are soluble except with these three things. So it's nice that there's those words, but they make it look more complicated than it really is. So let's do this and just see what the exceptions are. So silver, mercury 1, or lead 2. Mercury is a weird one. This is Hg2, 2+. We call that mercury 1 because each mercury atom would have a +1 charge. That's different than mercury 2, which is just Hg2+. I will not try to trick you with that one. Okay, just remember mercury. If it's mercury, then chloride, bromide, iodide would be insoluble. So those are three exceptions there. If you still haven't come to what you have, here's sulfate. Sulfates are soluble except with these things. So again, let's open this up a little bit here. Oops, didn't mean to do that. So we can just see the exceptions. Strontium, barium, lead, 2, silver, or calcium. Strontium, barium, and calcium are all in group 2, right? And then there's silver and lead. So if you still haven't encountered what you need, then you come down here into these are generally insoluble. So hydroxides and sulfides, insoluble except when they are with these guys. Okay, so I'm telling you, you should start at the top of the table and work your way down. If you come to one of those guys, you're not going to get down here. So do we need to remember this exception? No, because we're going to start up here. If we come to lithium hydroxide, we're going to say it's soluble and we'll be done with it. When we won't get down here and need that. So I'm just going to cross that one off. We don't need that. Sulfide, when sulfide pairs with calcium, strontium, barium, do those guys sound familiar? Those are the same ones that were an exception up there. Then these are soluble with sulfide. And with hydroxide, with those same three guys, slightly soluble. So slightly soluble, let's just call that soluble. There, does that look better? So if there's, oh, I don't need the, if you've got one of these three with hydroxide or sulfide, it's going to be soluble or at least slightly soluble. Last, carbonate and phosphate. Again, when these pair with lithium, sodium, potassium, or ammonium, start at the top of the table. If you've got one of those, you're not going to get down here, so you don't need that either. There. Well, it's not so bad. You should memorize this table. And one way to memorize it, you'll be needing to predict the solubility of things. Try to do it from memory, and then check yourself. Okay? But work your brain first. Okay, so we should be able to do this. Predict whether each compound is soluble or insoluble. So we're going to mentally think about that table. So nickel sulfide. So on this first one, we'll actually look at the table. So nickel sulfide, we're going to start at the top. We've got group 1A metals and ammonium. Nope, don't have one of those. Don't have nitrate or acetate. None of these. Don't have that one. Hydroxide. Sulfide. We've got sulfide, right? It's nickel 2 sulfide. Nickel 2 sulfide, generally insoluble except with those three guys. Nickel is not one of the exceptions. So we're going to predict that NiS is insoluble. So insoluble. Oh, trying to write with a white marker. Doesn't show up very well. Okay, this one. Magnesium phosphate. Well, we start at the top. And we don't find magnesium or phosphate anywhere in the top. So we go down further, and we find that phosphate is at the very bottom of that table. And what are the exceptions? There really aren't any for phosphate. The only exceptions for phosphate are the alkali metals and ammonium, but if we had one of those, we would have stopped up here, so we're not going to run into them. So the phosphate then, yeah, sorry, I'm probably making you dizzy or something. I'm making myself a little crazy. This is insoluble. Then this one would also be insoluble. About lithium carbonate. Soluble, because the first line, if it's got lithium in it, it's soluble, no exceptions. So we don't need to look at anything else. This one's soluble. Ammonium chloride. Soluble. Ammonium is also on that first row. Okay?